In this video, I want to look at a visual representation of an algebraic equation. And the best visual representation I can come up with for an equation is a balance beam. So let us put one big blue square on the right-hand side, and let us put two small purple squares on the left-hand side, and we'll pretend all the fulcrums are, all the lever arms are the same length, and the fulcrum is right in the middle, so we don't have anything complicated here to work with. When you look at this picture, you would clearly say that whatever is on the left must in some way be equal to what's on the right. With a balance, we would say that the weight of what is on the left is equal to the weight of what is on the right. But we clearly have different things on the left than on the right. Algebraically, we might say we have two of something that we don't know on the left, and we have one of something that we don't know on the right. But we would say that those things are equal to each other, whatever they are. Now let's consider all of the things we could do. If I were to turn around and add something to the left-hand side of the equation, let's just say we put something here that we know has a size of 1. Maybe it's 1 gram. You know that this would suddenly offset the equation. It would the balance would no longer be balanced. The equation would no longer be equal if I wrote +1. But if I turned around and put the same thing over on this side of the balance, it would suddenly be balanced again. This brings up something that we have to consider with order of operations when working with equations. If I have something that's equal, then I can perform addition to it as long as I add the same thing to the left side of the equation as the right side of the equation. Now I could also do the same thing with subtraction. If I took one unit away from the left and the right, it would work equally as well. It's hard to show taking away a unit. Now let's consider another case. Let me get rid of what I added to the scale here. Okay, restoring balance by taking away from both sides. Have to get rid of adding 1 on both sides of the equation. Shrink this up, and let's go back now to considering this. What if I took a second y and put it on this side? Clearly, we wouldn't have a balanced situation anymore. The right side would be much larger than the left. But if two of those purple blocks could balance one blue block, then two more of the purple blocks would balance the situation out. So what have we done here? We have a balanced situation again. But what we've done is we have multiplied both sides times 2, giving us a total of 4 purple blocks, x's, and we have now 2 y's. Could I now turn around and add a unit block? Call that a unit block. I could add a unit block over here. They're balanced again, so that would be true as well. So in this case, in the second case, before I added the unit block on, let me take that back off of there. Before I had added that on, I had multiplied both sides by 2. So multiplication is something we can do as long as we do it equally to both sides. If we doubled both sides, we still have a balanced situation. I think it's hard to illustrate, but I think you can, by comparison, consider what would happen with division. If I had taken the blocks on each side and cut them in half, the half that remains would be equal. So we can do multiplication and division to an equation as long as we do it equally to both sides. It will remain mathematically balanced.